What is software engineering? Well, according to Merriam-Webster, software engineering is a branch of computer science that deals with the design, implementation, and maintenance of complex computer programs. In other words,
software engineering is the study of getting computers to do what you want. It's making software that's reliable, that works every time, that is easy to change, and that costs little to maintain. That is the real challenge.
software engineering is a concept that was first introduced in the late 1950s. It is a very new profession, and there is undoubtedly much more in terms of potential and opportunity to be discovered on the subject. Right now, though, the most prominent or well-known part of the engineering process consists of devising a set of text commands which a computer can read and carry out to perform a certain function.
We've been building bridges for thousands of years, so we know how to do that. We've only been programming computers for 70 years, so we don't know how to do that well. And currently how it works is that you create a language that's close to English that you can translate into computer instructions that the computer can use, and then you try to characterize the problem that you're trying to solve in terms of those.
Without programming languages, you can't program, and without programming, you can't get a computer to do what you need. There are hundreds of computer programming languages, the first of which to be invented was a language called Fortran. Some of the more popular and highly used programming languages right now are Java, JavaScript, C, C#, C++, and Python. All are used for the purpose of solving problems and making our everyday lives more convenient, just like any other type of engineer would. Many people have questioned whether software engineering is a real engineering discipline, and whether a software engineer fits the standard definition of an engineer or not depends on which edition of the New Oxford Dictionary you're looking at. One of the biggest differences between programmers and people like mechanical engineers, however, is the complexity and fragility associated with their work. While mechanics use combinations of standardized parts with maybe loads of paperwork, certifying that they can perform a certain function or carry a certain load, software engineers have to be a bit more creative and adaptable. When using a programming platform, there's an element of trust that it can perform in the way it should, and that it's reliable as the provider claims. In addition to that, while mechanics often follow blueprints or designs comprised of a set number of standardized parts, no good computer program could possibly be constructed in this manner, with sometimes millions of lines of code which could all fail to work correctly because of one incorrect symbol. One of the most frustrating issues with software engineering is the project success rate. It's sometimes said that only 1/3 of all software endeavors produce something usable and efficient, while another third produce a product that works but isn't satisfactory, and the rest don't produce anything at all. This, though, the people interested in going into the field of computer science only continues to grow as the demand for software developers skyrockets as a result of the importance of online media in today's society.
This is something we should all be thankful for, because without software engineers, we'd be lacking an incredible amount of things that most people today would not like to imagine themselves without. Cell phones, desktop computers, tablets, apps, live television, gaming consoles and video games, Netflix and YouTube, cartoons and anime, cat videos, and don't forget things like automobiles, medicines, grocery stores, and even fast food chains.
Someone has to do the dirty work. So what does it take to get a product from the user's mind to the user's device? To get from the drawing board to the computer? Let's take a look at the stages of the software engineering process. The first stage is communication. The user or client requests a program of a software engineering firm or team. The team then gets to work on the next two steps, which go hand in hand: requirement gathering and feasibility study. Before actually creating the program, the software team must determine everything the software must do, organizing those requirements into their own distinct categories. If the program they desire to create is a new version of an old program, then the team will probably examine the previous version to take note of features that need to be improved upon. The team must then assess whether it is feasible to create a new program from a practical, financial, and technological standpoint.
Next, the team creates a plan for what path they will take in making the program requested that best suits the user's needs, taking into account the requirements of the program and the limitations of the platform in use.
They also must take into consideration the project scope for scheduling purposes. Once a path has been chosen, the team can develop a much more detailed blueprint for what the final product will be like. The software design stage, the team makes diagrams to represent functions of the program and comes up with both a logical and physical design, sometimes creating pseudocode, which is like regular code but written out in a more formal language. This is the last critical stage before the actual code construction.
Once the design is finished, the software team can finally write the code required for the functions of the desired program, trying to make an errorless and executable file in a programming language that is most suitable for the platform being used and the client's preferences. This is the step most commonly defined by the term computer programming.
The next stage, testing, is an integral part of software engineering that rivals the importance of writing the code itself. Both during the code construction and at every stage after, the team should run the code and check to make sure that every operation is functioning the way it should. After all, errors in programming can have any range of negative effects, including the complete removal of the program itself as a result of running it. It is estimated that approximately 50% of the whole development process should undergo testing.
Once the team determines that the program seems stable and unflawed, they enter the integration phase. During this process, they integrate, for lack of a better word, the program into an environment similar to that in which it will have to run. This is to make sure that the program will not cause damage to the environment or other programs within it when run. After the program clears the integration phase, the team moves on to implementation. At this point, the user receives the finished software and uses it for its intended purpose, assuring it has met its requirements and testing it for portability and adaptability, as well as making sure that no problems are caused during the implementation. If success has been achieved up till this part of the process, the user is instructed on how to properly use and maintain the program. The software team can also go back to fix bugs, errors, or inefficiencies which are only apparent when the program is used in real life, or edit the program according to changes in the user's environment, technology, or preferences.
The operations and maintenance stage is the final one, that is, until it comes time for disposition. This stage is one the software team and client must complete after much time has passed, rendering the program outdated and obsolete. At this point, the software needs to be completely remade or rethought, so they make arrangements to discard it and start anew. Then the process typically begins all over again with another project.
For those that may be lost, here are those same steps presented in a more user-friendly fashion. Client Joe says to the software team,
Write this code for me.
What do you want it to do?
Joe wants it to make a light turn red on Tuesdays.
Can we do that?
Well, last time we wrote 100 lines of code in a day, so we can probably do that. How can we make it turn red on Tuesdays without breaking anything? Let's write down exactly how we're going to make it turn red on Tuesdays. The software team writes the code that makes the light turn red on Tuesdays. Does the code tell the light to turn red when we run it?
If it doesn't, how can we fix it?
When we use it with the light, does the code make it turn red correctly without breaking anything?
If it doesn't, how can we fix it?
When Joe uses the code, does the light turn red correctly without breaking anything?
If it doesn't, what can we do to change it?
How do I use this code, and what do I do if something bad happens? I don't like this code anymore. It's old and it doesn't make the light turn red well enough.
The code is too old to fix. We'll have to get rid of it and start again.
So this is now. What about the future?
As of now, many predictions have been made about the future of computer programming and software engineering. Some people think that robots will eventually conquer humans and take over the world, while others deem that idea utterly far-fetched. However, it's actually beginning to get more difficult to differentiate the worlds of science fiction and science fact. Already, computer programs are being created which have the ability to observe, adapt, and learn. Some have been given names and personalities, even a kind of creativity. But is this development of software engineering really something we should be worried about?
Right now, we program the computers. A forefront of this field is getting computers to program themselves. And so this is actually pretty scary because once the computers are making the decisions of our society instead of us, it becomes their society. So we do have some decisions we have to make as a culture and as a people and as a species about how we're going to integrate computers into our lives, because big changes are coming.
So maybe we should be a little worried. Or maybe not. But one thing is certain. The demand for new software engineers is only growing. and the need for their work isn't going away anytime soon.
But it's a beauty, it's an intricacy that you really can't see. It's I'm a mechanic, where another mechanic can pop open the hood and say, "Wow, you did a really good job with how your engine is doing that thing," and they really get that. But all the driver can see is that it runs.
Some may consider it a frustrating, tedious, and most of all unappreciated line of work. With a large portion of the population oblivious to the effort that was required to make their everyday products, it can be a rather thankless endeavor. But software engineers are proud to bear that title, because without them, the world as we know it today wouldn't run.